Well, good morning. Thank you for tuning in. My name is Tom Manners. I'll introduce myself in just a few moments. Today we're looking at representation and a little bit more on algebra tiles, but certainly looking at negatives and the introduction of them and the four operations of them. So as a starter, whilst people were waiting, I asked people if they could represent 13 times 12 in many different ways. And of course, even the words I'm using, 13 multiplied by 12, 13 lots of 12, 13 groups of 12. And of course, multiplication is commutative. So that could be 12 groups of 13, 12 lots of 13. Really important to use lots of different language because pupils will connect to at least one of them. If we just use one, we're limiting our options. And there are quite a few options there. You can see maybe here with the Dean's blocks in the middle. Over here, the kind of representation then as an area. The grid method, which it extends to, of course, as well, which is why I like so much using representation for expanding brackets like we did last week. So the area of this rectangle here is 13 times 12. This rectangle in the middle, 13 times 12 is 156. But that can remind us, of course, the area of a rectangle when we expand brackets, which we will do a little bit of a reflection of last week shortly. You can see in the top right here, there are, what, 13 12s there? And then below it, you can see 12 lots of 13. Again, the importance of multiplication and commutativity. Representation can really make it come alive for pupils. The bottom left gave me a bit of a headache, but eventually I could start seeing there are lots of 12s there. But hopefully you found that interesting. Okay, that was taken from @StudyMaths. If you're not a Twitter person, I thoroughly encourage you to do so. You can follow me and I'll give you my handle in a moment. But this guy is the one who's created MathSpot. Absolutely brilliant. He shares some superb resources. I'm going to make some recommendations today as to some websites, but also some people to follow. So thank you for tuning in. My name is Tom Manners. That's my Twitter handle @Mathematics. My very first class came up with that when I said I'm joining Twitter, and they created that for me. So I still love them for it. That's what I look like when it's pre-lockdown, when I'm getting other people to cut my hair and I'm shaving. So that's what I normally look like anyway. Now, I work for myself. I don't know why that's come up at the bottom of the screen. I work for myself a couple of days a week, but a lot of what I do comes from my work with the NCETM. So I work for them as part of my 2 days as a Teaching for Mastery specialist. If you've seen one of my previous videos, I talk about, let's just say, the inconsistency of the word mastery. But I'm lucky enough to work through the Central Maths Hub, which means I go and share my ideas, my knowledge, and share what the NCETM's 5 big ideas are, and very much enjoy doing that. I'm also a subject pedagogy lead for maths at Arthur Terry School in the West Midlands. Means I train teachers. It's a job I always wanted, to train teachers. And I love working with new teachers in the profession, but also staff who've been working for many years as well. So I'm quite fortunate that I do 3 days a week at Arthur Terry. Then the other 2 I get to go and visit other schools. But it also gives me the time to really focus on pedagogy. And that's why I wanted to share that during this lockdown time. It is my passion, and I sit here and I'll enjoy the next 90 minutes. This doesn't feel like work whatsoever. I've also been qualified as an NCETM PD lead. And if you're interested in that kind of thing, by the way, the NCETM are advertising now. If you want to try and get that kind of qualification, almost an extension to an SLE role, well worth applying. That's just come out, applications in the last week. This is, by the way, being recorded on the 1st of May. If you know nothing about the maths hubs, as you can see there, 37 hubs currently. By September, there'll be 40 of them. And my advice is to join the mailing list for your local maths hub. So mathshubs.org.uk. Go and have a look on that website. See your local, where your local hub is. There's loads of free training. And everything I'm going to share from you today has been inspired by the maths hubs and my connections with it. I knew a certain amount of stuff, but it's absolutely opened up my mind in the last 2 or 3 years. These are the 5 big ideas that we talk when we're teaching for mastery. You notice every single time I will do the inverted commas. And we are focusing on the top left-hand corner, representation and structure today. Representation and structure exposes the structure of the maths. In other words, the kids don't just see the numbers like they usually do, and they just don't see the letters, the algebra. We can actually show them what it means so they can try and actually have some better understanding of it. It can pull out the concept being taught and what's key difficulty. And there'll be key representations which students will meet time and again. So not just bar models. We'll meet at least 3 today, if not 4. And I advise you very strongly, and I will mention it a couple of times today, along the lines of the right representation for the right situation. It doesn't mean bar modeling is great for everything. In fact, I had an email from a colleague yesterday asking about negatives on bar modeling and struggling with it. Pattern and structure are related, but they're different. You might see a pattern, i.e. an algorithm, but not understand why it's working. And we know on the first fluency on the national curriculum, it talks about conceptual understanding. We've got to understand the structure. And this is a really, really important line. This is not to replace the abstract form. Kids still have to do the exams in the form they get given it, in the abstract form. Students need to be able to do the maths without the representation. And that's why this is really important, why we talk about the CPA approach. The concrete, the manipulatives they get to play with, the pictures they get to see, and then the abstract they've got to do. It's a journey to get us to the abstract. It certainly isn't to replace the abstract. And that's really, really worth pointing out at this early stage. If you haven't seen this document, the Education Endowment Foundation have made this very useful booklet. In fact, it's next to me. Improving Maths in Key Stage 2 and 3, well worth having a look. And number 2 there, use manipulatives and representations, well worth having a look to see if you're working with your own practice, but working with your own team. I showed this last time as well, but the bottom right is the one thing I'd like to really go to. It can be used to support pupils of all ages. I know someone in the last session talked about their GCSE resit class, and I would restart it with Algebra tiles, absolutely. The National Curriculum's assessment objectives, I just referred to them, and there's those key words there, the conceptual understanding, and that's why we're going to be doing a lot of representation today. Reasoning, of course, is the next level up, if you like, and then solving problems. I love the words on the reasoning. Mathematically, they're conjecturing relationships. And I've just seen we've hit 100 on the participants. Fantastic. Developing an argument, justifying, using mathematical language. Look at those words there, using mathematical language. So I'm going to challenge the language that we use in our classroom, certainly around negatives, not minuses. Around negatives. I'll just get that out now. And next week's session is about speaking like a mathematician as well, and I'm really looking forward to that one. A few reminders, that's what I look like. That wasn't the reminder I wanted. This session is put together by me, and the ideas are shown and my interpretation. In other words, I'm not representing the NCETM today. I'm not necessarily representing Arthur Terry, my current school. I am representing me and what I've learned from all these different places. I hope you're going to find the ideas interesting. I hope you want to use some of them, but actually I want to reiterate this, like I said last time, I really hope you don't like some of the stuff and you think, actually, I want to use it in a better way. And that's fantastic. So if you're thinking about your own pedagogy and trying different stuff, do you know what? That means I'm making a difference, and that would be amazing. So here we go, Algebra tiles session 2. We're looking at integers today. We're going to do some substitution using tiles and solving equations. If at any stage you're enjoying it, please share it on @Mathematics. That would be great if you could. If you're not enjoying it, that's not my Twitter handle. I'm lying. So a quick recap from last session. What are algebra tiles? They're these tiles here. We have 1 tiles, which I'm just going to move the cursor over so you can see. You have 1 and -1. You have x tiles here, and you have x squared and -x squared. And x represents a variable. But I think the really key line here is flipping a tile is the same as multiplying it by -1. Again, it says here the NCETM have created a series of videos on algebra tiles, and my session on algebra tiles is available on YouTube now. The knowledge of the dimensions are crucial to their use. You will notice there that the x tile has a width of 1, so the 1 tile can go on the end, and of course a length of x, so it can fit onto the x squared tile, really important. And one of the things we referred to last week, the length of the x tile is irrelevant. Teachers, you must make this really, really clear. It's still a variable. The width of the x tile is 1. Now, this came from Yip Van Ha, which was a really interesting concept for me to understand. Yip Van Ha is the main guy behind Math No Problem. And if you ever get a chance for him to speak, go and listen to him. 5 equals 5. So therefore, 5 take away 5 is 0. And that then starts to make us realize that 1 and -1 cancel each other out, and we create these 0 pairs, and I'll show you a few of them in just a few moments' time. They won't affect our calculation, no matter how many 0 pairs they've got, they are worth 0, they affect nothing. And I said this last week, which I wanted to reiterate at the start as well. The major thing to consider when using these tiles and representations is take the time to ensure pupils can show a range of expressions using the required tiles. Do not rush into them saying, this is x, everyone happy? Good. Get them to show you x. So let's do a few examples. So show me x plus 3, and they'd show you that. But then you ask them to show you x plus 3 another way. Now, actually, I could have rotated that. Maybe I should have done. But I've still got x plus 3 on my second picture there. That 0 pair has not changed the value. It's still x plus 3. And the kids have really got to understand that that 0 pair doesn't change the value. Let's try another one, x squared plus 3. So that by doing that question onto x squared plus 3 from x plus 3, they'll be making sure they know the difference between x and x squared and how it's represented. They are different things. Then, of course, x squared to x squared plus 3x. Brilliant. And there it is, so they can see the difference, that 3 is not the same as 3x. We know these problems we get with algebra, and this is a really good opportunity, early doors, to make sure the children understand the difference, that they're not the same. They are not like terms. And show me x squared plus 3x again. I put a 0 pair on. Who cares? I'll put another one. Doesn't make a single difference. I maybe should have put on an x and a negative x together there. That would have been nice. I wish I'd planned that now. Making connections with maths is very, very important, again, in the national curriculum, but it's all about what we know about the science of the brain at the moment. Now, if we're making connections, it makes those schemas stronger and those connections stronger. And what we're doing connecting here is showing that x plus 2 times by x plus 4 in the bottom left here. It's the area of the rectangle creates x squared plus 6x plus 8. And we're making connections with area of a rectangle to expanding brackets. And the connections in the brain, this image taken from Craig Barton's great book, all these new kind of ideas of that are coming into the brain. You see the connections are being made, and therefore in the schema they're becoming stronger. What I would say, there was a really nice quote in that book, which I really like, from Willingham, that learning is just another form of remembering in disguise almost, because if we've made those connections to previous stuff, it's building on the previous knowledge, and that's always really important in mathematics. I've just referred to this. Factors of a number, an area of a rectangle have in common. So we've got 3 and 5 are factors of 15, because we can make them an area of a rectangle of 15. So we talked about factorizing a little bit last time. And here we go. If I can make a rectangle using the terms involved, so the terms are 2 lots of x squared and 16 x's, I'm able to make a rectangle of them, and those factors are created, 2x times x plus 8. So then, that was going through some of the stuff from last time. I know I've done it quickly. Hopefully some of it's gone in, but if not, again, that previous video is there. Amy, any questions at this stage or complaints already?
No, real good.
And another reminder, if you've got any questions throughout, Amy's reading that for me, producer Amy, who you used to work with. So thank you, Amy, for doing today. But any questions, do shout them out for me at any stage. So let's look at integers. The language and representation is very important. And now, I've seen this in lots of different ways, but this textbook is something you can download it. It costs, I think, about 30 quid. But I was advised it by someone from the NCETM, and I thought it was really interesting to look at, because it really made me consider integers and how we look at them. Now, grade 7 is secondary, but I think the introduction of integers comes in this book as well. So it's certainly going to be relevant to our primary colleagues listening today. And I looked at some of the things that they're introducing, and it said understanding what this sign means, the plus sign. This sign, it says the negative sign, or is that the minus sign? And I'm going to question that, actually, because in the book at the moment, that's the minus and the negative sign look the same. But there's a lot of kind of historical use that they're not the same. So we'll come to that in a bit. So one of the first things when we're introducing integers is making it real life. And for those of you who, the top right, who may be football fans or just league systems, you can see teams who are in goal difference. And they've had more goals against them than they've scored. And then some children will recognize that before and say, oh, yes, of course. And so 2 is very different to negative 2. Tomorrow's weather, taken from the book as well. And, it gives me rage. And 90, well, how many people in the room at the moment? 102. I'm going to bet that 101 of you, when it gets cold over winter, at night time, you say, oh, it gets to minus temperatures. It gets to -3. We're not helping people. That isn't actually correct. It's inaccurate. Minus is the act of taking away. Minus is not a state. It's not an adjective. Minus is the act of taking away. So are we taking away 2 in Yamagata overnight? No. The state is -2, and so the country have got it very, very wrong. And one day I'm going to fight the BBC, and I'm going to win, because it's not -2. It should be -2. And we've got to think about that in our classrooms. And so negative and positive, they're a state. They're an adjective describing a noun. And minus, subtract, or maybe take away, they're an action. It's an operation. It's something we are doing. And I think that's really, really important. When I hear the sentence 2 minuses make a plus, I want to grab something and throw it at the screen, because there's no understanding going on there. They're using a trick, and also they're using the wrong language. 2 minuses do not make plus. 2 minuses is just one big, remembering it's being recorded and it can be played back later. So I'll watch my language. But Anne Watson, I noticed on Twitter a couple of days ago, people arguing about minus versus negative again. And again, if you're not on Twitter, one of the big pieces of advice I received was there is so much good pedagogy on Twitter. So my personal advice is join it. There's a lot of arguments sometimes, which is a bit of a shame, but there we go. The NCETM glossary is available. All you do is go onto Google, type in those words there, NCETM glossary, to help us ensure common language. And so I looked up on the mathematics glossary for teachers in key stages 1 to 3, because I thought, interesting, today if I'm going to do minuses and negatives, I said minuses, And I thought it was worth just sharing this. So what does minus mean? A minus is a name for the symbol representing the operation. Aha, there it is. It's a verb. We are subtracting. Subtraction is the inverse operation to addition. It's the opposite to addition. Finding the difference when comparing magnitude. Now, magnitude is a really interesting word, which I want to talk about a little bit later on. And then I thought to look at the word negative number, a number that is less than 0. We have numbers that are greater than 0, not bigger than 0, greater than 0, and we have numbers that are less than 0. And the example they've given is a decimal one, interestingly. Commonly read aloud as, now I don't like that. Why don't we just say should be read aloud as -1, or not -2, it's -2. That's not right. In fact, I'm going to write a strongly worded letter when I finish today's seminar. Some of my ideas today have been taken from this brilliant video, and what I'm going to do during the, I've asked Amy to share some links. If they're not shared during the session, we'll share them at the end. Really good video with Craig Barton. If you don't listen to his podcast, then you should. But he did one of them where he did them on YouTube because they wanted to see manipulatives. And the Bernie Westacott video with Craig Barton is really interesting. I thoroughly enjoyed watching that. And some of the ideas I'm sharing today definitely were influenced by that video. I don't know why. Oh, in fact, you know what? I'll come back to that crocodile there. So it's time to go on to me and go on to the camera. Now, hopefully, can you see my my camera now, Amy? Me drumming my fingers.
Yeah, we can, yeah.
Brilliant. Okie dokie. Any queries, complaints so far?
No, we're all good. I've just posted the YouTube link if people wanted to have that later.
Now, of course, in the classroom, if you give kids the opportunity to go and do something else, they'll go and do it. So don't go and watch it now. You can watch it later.
It's for later.
It's for later. It's not for now. Put it down. Right, okay. So I've done a number line, and I've gone for vertical. Now, this was...
Oh, Tom.
Go on, then.
Just one question.
Yeah.
What is the hang-up with the bigger than compared to greater than? Someone's noticed White Rose Maths scheme of learning is really big on using greater than. Could you just elaborate on that before you move on?
I was going to, but I'll do it now. Tell you what, I'll just go on to a new screen. No, I was going to come up, so it's been enough. Let's do it now. Right, which looks bigger? Amy, you're going to be my you're going to have to answer questions for me. Which looks bigger? The yellows or the reds?
The reds.
Exactly. Now, actually, at this stage, I'll tell you that yellows represent +1 and the reds represent -1. So if I ask you again, which is bigger, by using that word bigger, the bigger creates almost like maybe a relationship with area, but bigger, I can see it's bigger. But actually, that represents a smaller number. And I think what they're trying to do is a lot of consistency. And I think when you look at Singapore Maths and Maths No Problem, they're very, very particular about that language as well. It's actually quite consistent. It's nice to hear that White Rose Maths are doing the same. So I think greater than is when we're comparing numbers, and we'll look at, you do it alongside the number line. But bigger than, I think the reds look bigger. In fact, you just said it, the reds look bigger. So I think it's kind of it's kind of important there to make sure we're consistent from class to class. We don't always have the same teachers. That's why I speak about a lot of consistency in schools. Hoping that answers the question. Answers that one anyway. Right, let's move some of these tiles out of the way. Now, I could have been using algebra tiles, and I've got them right here. But actually, I'm going to use the counters because actually they're easy to manipulate. Amy, go for it.
Sorry to interrupt you again, but just going on back to that point. So bigger could represent magnitude.
Yeah, I'm going to talk about magnitude and size a little bit later on. But I mean, again, we look for consistency across the classrooms, and greater than is certainly more popular language than bigger than. And so I think it's because when we're going to compare positive and negative numbers, -5 looks bigger than 2. But so suddenly it's like, well, it must be bigger. But actually, that's why we're trying to make sure we use greater. Where is it on the number line? So we're going to relate the integers that we see to the number line. And again, that goes back to the concrete pictorial abstract approach, that actually it's to get to the abstract, concrete pictorial abstract. It's not to replace it. It's a journey to get towards them. We've got to maybe make the relationships between the two regularly. I mentioned Twitter on Maths Mr. Gordon and at Study Math. They both do a lot of sheets where they're doing the representation and the abstract next to each other, because the connections have to be there. They're not supposed to be separate. It's part of the journey. So I'm going to make a number line, and I've gone for horizontal purely because maybe you'd see a kind of a ladder of a thermometer, for example. I don't really have a massive preference over these, but I think it's really important just to show that we have got a smaller, you could say you've got fewer discs, using the proper word, not less discs, but fewer discs, because we can actually count them. Remember, this thing here is a numeral that represents the number. There are 4 discs here, and they represent 1 each. And this numeral here, 4, represents the 4 that we can see. This numeral here, 3, represents the three discs we can see again. And again, at the moment, you can see what's happening. So 2, and I wish I'd made these a little bit bigger now. Look at that. I'm going to struggle, aren't I? I might just draw a new one in a second. Do you know what? I think I should, before it gets confusing. So I've got 4, 3, 2, and 1. So 4, 3, 2, 1, 0, negative 1, negative 2, negative 3, and hopefully we can still see that. Now 0, there are no counters, no positive counters, but negative 1, there it is, and negative 2. And at this stage, I think that's really, really important. And so we start doing those questions. And just like I think when Key Stage 1 staff would introduce comparison of number, which is greater, 4 or 3? Why? Convince me. And you might say there are more of them, and that's where people might use that language. In the concrete, we can see there are more of the yellows. Okay, so 4 is greater than 3. And in fact, we can see on a number line, so if I just draw a little number line here, 0, while we're going that way, while we're going to the right, the numbers are greater. And that's just making those links between the physical items and the number line. So it's not just using the apparatus, if you like, the manipulatives, we're using the number line as well. And so 4 is to the right of 3, and it's a greater number. 4 compared to 2, which is greater. Convince me, a lovely couple of words you can use in the classroom, AO2 reasoning. Convince me 4 is greater than 2. Convince me 4 is greater than 1. Convince me 4 is greater than negative 1. And what about when it gets a little bit bigger? So which is greater, 2 or negative 3? If I move it along so we can see that. Now we've then, by making those questions, continually referring back to them, we're not rushing, but comparing 2 to negative 3 is going to be where the sticky points begin. But if we've been quite consistent, saying, well, 2 is to the right on the number line, well, actually, 2 is bigger than 1, 2 is bigger than 0. 2 is bigger than negative 1, 2 is bigger than negative 2, 2 is bigger than negative 3. And so we've got to make more and more clear, if you like, that the negatives are the opposite. I know we use the word additive inverse sometimes, but I'm going to use opposite in a few moments, so I thought I'd use it now. 2, when it's red, when it's positive, it's going to be opposite behavior to when it's a negative number. And so we can see greater than, not bigger than, hopefully, and making this idea that it's greater when we go to the right. And that's really, that becomes really, really important. Now you might say the number 2 is smaller than the number 3, and the number negative 2 is smaller than the number 1, but you'd say 1 is greater than negative 2. And so I think they're just trying to making sure, I mean, consistency, I fully believe in. Okay, I'm going to move on to another section of this, and some of these ideas were definitely influenced by the Bernie Westcott video, and well, I have ideas in my head, and then when you hear somebody else talk about it, and maybe it kind of forms a bigger image. And let's make the number 5. So I'm going to make the number 5. And there it is. You know, you ask your pupils to make that number. And how would you make a number 1 more than 5? And again, when you're introducing the whole numbers initially, this is the kind of standard behavior you do in the classroom. Well, you make 1 more. You add another counter. 5 plus 1 equals 6, and it's represented there. Can you make me a number 1 more than 4? So I'd do that, and I'd make 1 more by adding 1 yellow counter. How about then 1 more than negative 4? And I think, now this is where I think using the concrete materials, the manipulatives becomes really important. Because if you ask people to add 1 more to negative 4, I think this is likely. And that's where we've got to start making it clear, actually the opposite begins to happen. 1 more than negative 4, and we go back to our number line. So we did 1 more than 4, we went over 1, and we landed at 5. And so adding 1 more, 1 greater if you like, it's going to the right hand side. Now I see no reason why secondary colleagues, if they're not ever sure that their children have picked this up well enough, then why not go back to this? What is 1 more than negative 3? What is 1 more than -4? And there you go, I'll put -3 on again just to match the number here that I'm using on the number line. 1 more than -3, the instinct is that, but in fact the truth is that. And when we talk about 0 pairs, and that becomes really important, of course they disappear, and now we've got this number -2. And when it gets greater, as we said about going to the right on our number line, and we're making this connection concrete, pictorial, and abstract again, is to get us to the abstract, certainly not to replace it. And there's a pause there, isn't there? So let's just go back to that a second. -3, 1 greater number. Again, the kids have to think about that, and there's a good chance for a conversation on that reasoning in the classroom. I think I know he refers to it in the video, but it's an expression I use a lot. So much so that it's on my wall at all times. Memory is the residue of thought. Willingham, 2010. If you've got the pupils to think about the action there, it's not just shove the red down. It's actually still in an additional yellow to create that 0 pair. The number goes from -3 to -2 if I'm making 1 greater. It's a reminder that the negative is the opposite of positive. Do you think this would be as effective without the counters? And I'd argue not. I think actually having these counters and the visual side to really represent that, I think is really important. What's it need to make a number more negative? So if I want to have one number smaller, if you like, than -3, -4. So when we say 1 less than, maybe, because we're now going to look at the counters. So what's 1 less than? So I've got 1 less than 3. I'd take 1 away to be less than 2. What's 1 more than 3? And we're looking at that comparison maybe, and maybe we start to introduce the idea of comparisons. And that's why I think a moment ago I showed the crocodile. Deep breath. We'll cover the crocodile in just a few moments. But what is 1 more than -3? I thought hopefully that's been quite interesting. So there again, so the question came in on the chat before, which is greater, 4 positive ones or 6 negative ones, and I'll just put them on screen, which is greater. Then there's a conversation to be had, and again, representing it, comparing it to the number line, really, really important. Okay, what I want to do is just go back to this, because this is a common thing that we often see, and we've got to understand why people use it. I think the reason people use it is because they want to make it a bit of fun in the classroom, but is there an understanding going on? 8 is greater than 3 because the hungry crocodile something. And the problem with it is the fact that kids don't remember what does the crocodile eat? Does they want the bigger number, they want the small number? And also there's no understanding there. Interestingly, this symbol, the symbolization there, we've got the representation there that 4 is greater than 1. Now, a question I think would come up very, very quickly on this is, well, how do you do that with negatives? And the way I've always seen it is, well, hold on, if you've really made this secure at the early stage when we're doing whole numbers, that the direction of the arrow, we can see there that 4 is greater than 1. Well, actually, you'd be saying, look, what have we learned before? The rules are still the same, and I'm going to go back to my camera here, that where it is further along on the right-hand side on the number line, it is greater. So if I did have 3 and -7, well, when I was learning about this arrow here, I realized that the number here, let's say x just for fun, anything x is greater than 3, it'll be all these ones to the right of 3. -7 is to the left of 3. So -7, 3 must be greater than -7. So it isn't an easy one to represent. And I used this sentence earlier on. I'll use it a number of times today. The right representation for the right situation. But with regards to that crocodile, this is where it comes from. You can see 4 fit in the arrow, and it's greater than 1. So this word's idea of minus or negative. Now, can you see where the symbol before the 1 is? And just give you a chance just to notice that it's a little bit higher up. And I've seen that in quite a few books now. And I'm finding that really interesting. Are we doing it wrong? If we keep the negative sign like the minus sign, then of course there's confusion. And so you might, as an individual, want to teach your class that actually the negative sign, we write it a little bit higher up. And so we can see minus, the subtraction, the action, the adjective, versus the physical state, the negative, sorry, the adjective of the noun. The adjective describes a negative state of the number 1 there. The minus, the act of taking away, the subtraction. Interesting that they have been represented differently, and we've gone back to maybe them being the same, which is in most books, it's certainly interesting. Any questions at the moment? Everything all right, Amy?
There was just one suggestion, going back to the algebra tiles.
Yep.
When you placed the negative, perhaps putting it underneath so they could clearly see those 0 pairs.
Okay, I'm going to the camera. Can you repeat that? Sorry.
So when you had, for instance, I think the question was, you had -3 and you were adding 1.
Oh, got you. Okay, so -3. Yeah, brilliant.
And then you're to place the 1, the positive 1, under rather than next to.
No, great idea. So in other words, we were talking about what's 1 greater than -3. Well, actually, it was always the action. That's the instinct. This is the necessity. And by putting it there, I mean, a 0 pair can exist in that form.
Yeah.
0 pair could exist in that form. But yeah, absolutely right. I think we'll tend to do it 1 above. And when you do it online on the computers, you put one on top of the other and it disappears. Now that becomes a little bit confusing because when you put one on top of the other, you can't actually see the red anymore, can you? So that becomes a little bit of a thing to challenge. But yes, there's that 0 pair. And if we talked about 0 pairs a lot, there is 2 on screen right now. I'll put another 0 pair. Brilliant. Tell you what, I'm going to even go nuts. I'm going to grab the algebra tiles. There they are, 0 pair. So I've still got -2 on my screen. Yeah, nice idea about the way you represent it. But putting it on top of each other becomes those issues. Go on, sorry.
Yeah, a lot of people are noticing the impact moving them around with the tiles has, which is good.
Awesome.
There's also a comment MathsWiz uses 2 different signs for minus and negative as indicated.
That's nice to hear. That is interesting. And please, if you've got any kind of comments against what I'm saying, please do argue. I think the point of these top sessions isn't for me to say what you should do. It's for us to discuss what we should do. It's difficult on this kind of format, admittedly. But I don't ever want people just to go away and say, oh, I'm following this because this bloke on Twitter said so. It's about us challenging our thinking and how we do it best. So any thoughts, and certainly seeing that on MathsWiz, that is interesting. Now, interesting, give me just a moment, Amy, if you would. Those representations there, the minus sign and the negative sign, I was reminded by that by an old Teachers TV. Who remembers the Teachers TV videos? It was Anne Watson who shared it, actually, so I watched it. And I've given the link to Amy, so Amy, if you could share that later on. He taught the presenter on there talked about the difference between them. He said about the adjective and the noun as well, which I really liked. Go ahead, Amy.
Just another question before you move on. How would you show, for example, 3 minus -2? Can
we come to that later?
Of course.
Okay, we've got that coming up. So at the moment, we're doing adding and subtracting shortly. I love your I love the fact you want to know now. Thank you, whoever that was. Now I referred to this Japanese textbook earlier on, so I wanted to look at it. Now at this stage, we haven't done any addition or subtraction of negatives, but they're doing the comparison. And you talked about the word size earlier on. I heard the word magnitude, I think. You used one of those words anyway, Amy. If we express a temperature going up 5 degrees from the current temperature as +5, well, what does -3 or -3 Celsius express? Now, interestingly, we start talking about movements. Now, can you see from A, 5 meters to the right, and -3 or -3, 3 movements to the left, 3 units to the left. And so we're beginning to realize that size, and I think size is really important. I'm going to do a slide that I haven't seen other people talk about enough. And if people do talk about it, it's great, but I certainly never heard it. I'm going to come to a question that I challenge people to use in their lessons soon. Choice of language, so it becomes larger or greater. Interesting, that's used larger in the textbook. That is interesting. We talked about that. Greater is being more commonly used, but this Japanese book's gone for larger. But this is the question that I challenge people to use, and I think this could be used in all ages. What's the same, what's different when you look at those? And even that, if they've been talking before that yellow represents +1 and red equals -1, then I think we start talking about what kind of answers will pupils give, what would we want them to start thinking about. I'd want them to realize that the size of -3 is actually the same as +3. And I think that's really important. And so I'm going to quickly just bounce over to the camera here because it's just been pointed out. If you've got 4 plus -3, we get this answer as teachers, don't we? -7, and that's because they've heard a positive and a negative, or a plus and a minus makes a minus. Now, how can the size of that -3 can only mean 3 movements across? Okay, so let's start at 4. That -3, the size of that, the absolute value of it, if you like, or the modulus, if we're going to talk Key Stage 5, and I'll refer to that in a minute, it's only 3. So you could only go 3 that way, or you could only go 3 that way. How on God's green earth do you end up at -7? If you understand the idea that that -3 here, the size of it is 3. It's just talking about the direction, whether it's getting greater than or smaller than. How can you end up at -7? It's ludicrous, and it shows the people who give us that answer have no conceptual understanding of what's going on in this sentence. I'm getting excited here. They've got no conceptual understanding. They've just learned an algorithm that says, positive and negative makes a negative, and it completely takes them down the wrong path. So let's go back to that question that I put on here. What is the same and what's different? Lovely questions, those. And again, that's been heavily influenced from my work from the NCETM. Just putting stuff on screen, getting the kids to reason, looking at those two there. And I'd want them to recognize that the movement for +3 is the same as the movement for -3. And that's a really important concept before we start doing adding and subtracting integers. But I think that's really, really important. But yeah, I wanted to get excited about that there. Okay, now I used a word here, absolute value. And we don't use the word absolute value, I don't believe, before Key Stage 5. We don't talk about the modulus or the positive value. But isn't that important to think that the positive value of -3 is 3? There's something comparable about the same. The size of the two is actually the same. It's just about the distance. And there it is in the Japanese textbook. That's where I knew I'd seen it, and I found the book the other day. I was really chuffed. And this is something they've done at the very beginning. They certainly haven't done any adding or subtracting of integers or anything like that yet. But we know that the size, the absolute value of -3, as represented on this number line here, and again, take the manipulatives, the counters you're using, refer it to the number line, concrete, pictorial, abstract. The distance, if you like, the absolute value, the modulus, they are the same, negative and +3. I think that's really, really interesting. Why do we only use those absolute value words in Key Stage 5? It's in the top left-hand corner of your calculator that you start using. Still. So find the and so before they even move on, again, look at this. This Japanese textbook was doing this. Find the absolute values of the following numbers. The size of +8 is 8. The size of -10, if you like, is 10. I'd be interested to see if people argue with me using the word size. That would be interesting. The -2.5. Well, it moves 2.5, but not in the positive direction. It's not got greater. It's got smaller, but the size is still the same. What an interesting question there. Give the numbers whose absolute value is 7. For positive numbers, the larger the absolute value, the larger the number is. And this is something we see in Maths No Problem, in Shanghai teaching especially, actually, when I think about it, not Maths No Problem, but in Shanghai Shanghai lessons, they have this sentence on the board, and it'll always stay there on the board to refer back to, because that's the key learning point of the day. I've left that other screenshot from this Japanese textbook as well. Thus, using inequality symbols, the following is expressed. -15 is less than -11. And there again, that sentence would be, maybe some classes might do chanting, and the pupils respond back to you. For negative numbers, the larger the absolute values are, the smaller the numbers are. Now, of course, that's counterintuitive, but we've explored with the tiles, we've explored with the counters, and that then becomes hopefully a bit more concrete. So we get to adding and subtracting integers, but I'll just quickly check, Amy, if there are any problems.
All good.
Lovely. So then, adding and subtracting, I've kind of jumped ahead of what I was going to do, because this 4 plus -3 thing, I was going to come up with it later on. Now, there are NCETM videos available to help you develop your team. And so what I'm going to do, I want to show you a couple of those today to make sure you're aware of them. So you're not just having to use this, because this is freely available on YouTube afterwards. So obviously you can take this away and please use it with Teams. But I wanted to share the NCETM resources. So we're going to watch some examples of adding and subtracting integers from, and this link will also be shared with you in the chat a little bit later on. But let me go to this video here, using algebra tiles. So you could use counters. Please don't, I think they're easier to manipulate, to handle. So you might want to use them. But let's have a look at adding and subtracting directed numbers or integers using 0 pairs.
How can we use algebra tiles to add and subtract directed numbers? Let's look at these different ways that we can use algebra tiles. First, let's see what 0 pairs are. Because the reverse side of an algebra tile represents its additive inverse, we can use the 1 tiles to represent calculations involving directed numbers. Combining a tile with its red counterpart represents a value of 0 and is called a zero pair. Now let's look at identifying zero pairs when adding directed numbers. We can represent the addition 5 add -2 using 5 1 tiles and 2 -1 tiles. There are 2 zero pairs. As these have a value of 0, we can remove these tiles. This leaves 3 +1 tiles, representing a solution of +3. We can remove tiles to represent a subtraction. For the subtraction 4 subtract 3, we start with 4 +1 tiles. We then remove 3 tiles to leave 1 +1 tile, representing a solution of +1. We sometimes need to add zero pairs when subtracting. Let's look at an example. For the subtraction 4 subtract -3, we need to remove 3 -1 tiles, but we only have 4 +1 tiles. We can add 3 zero pairs without changing the value of the number sentence. We can now remove the 3 -1 tiles. This leaves a solution of +7. Similarly, with the subtraction -4 subtract -5, we start with 4 -1 tiles, and we need to remove 5 -1 tiles. By adding a zero pair, we can make this possible and obtain a solution of +1.
Think about the action, the verb, taking away.
Let's look a bit closer at how we subtracted -5. To subtract -5 from -4, we only had to add 1 zero pair because we already had 4 -1 tiles. However, the minuend can take any value, so it's important to understand that when subtracting -5 or any negative quantity, we can add that number of zero pairs and then remove the negative ones. We can see that subtracting a negative amount is equivalent to adding the same positive amount.
Making connections.
Let's remind ourselves of how we can use the 1 tiles when adding and subtracting directed numbers.
Let's leave that on screen for just a moment. So it reiterated some of the work with zero pairs, but I think what I talked about earlier about the verb, the action of taking away -5, you're actually taking away 5 -1 tiles. And so we're getting that idea of separating the verb to the adjective. I think that's really, really important. Right, let's go back to where we're on screen. I think it's...
Before you start, Tom,
yes,
there's just a question regarding when to introduce this. So if you were taking over a new class in Key Stage 4 who hadn't seen this before, would you begin to use it then?
Okay. With regard to introduction of all these representations, so obviously we did some the introduction of algebra tiles last week. My advice personally is you've got to make sure kids can use these as early as possible, and you will have some classes who will be a little reticent to using them if they're in year 10 because, oh, this is baby stuff. And it's a shame. It's just because if they haven't got the concept yet, well, do you want them to have a conceptual understanding? So in answer to your question, do it. Do it for the year. If you say to the kids, it doesn't matter what age they are, it'll be harder for the year 10s to take it. They've got to year 10 thinking, oh, I don't want this stuff. But if they haven't conceptually understood it, then you could just make that promise to them and say, well, just give me 60 minutes. Give me 60 minutes to try and show you how this will work and how it will convince you. So my personal thing is, Key Stage 3 coordinators who are listening today or year 7 teachers, you start using representation, you start using the manipulatives immediately. And I'll tell you one reason why. The primary colleagues listening at the moment are turning around saying, well, why aren't you using them? We use them in primary schools. We use them all the time. Why is it when you get to secondary school, you change mathematics? That's ridiculous. So, and again, feel free to correct if I'm wrong and do shout at me. But there are more primary schools using manipulatives, and the kids are used to doing that in math lessons. So when they come into secondary schools, oh, we don't do that stuff anymore. Well, why are we changing maths? And so the earlier the better, quite frankly. If you've got a year 10 class, they might be a little bit difficult to, they might not immediately want to do it, but it's up to you whether you think you've got that relationship with them.
Thanks, Tom.
Hopefully that answers that. Brilliant. Okay, so adding and subtracting integers. Yes, so just to refer back again, you saw the addition. It's almost referring it to the number line. So using those tiles and saying that you added 3 and moved 3 then to the this one here, this first movement, adding 3 to the right, then 5 to the left. And what they did here, investigated addition of positive and negative numbers. So adding 4, adding another 6, -4, and adding another -6. So relating those tiles to the movement, to the number line, really, really important. Let's do this example. Let me just remind myself what the words I was going to use. Excellent, because I had this, in a particularly good Blue Peter style, I had this sheet removed earlier on. So I did refer to this question a little bit earlier on, but I'm going to use different numbers this time. 7 add -4. I often talk about the start point. And in that video, I thought that did something very nice. What are we starting with? We're starting with 7 counters. Should have chosen a smaller number just to make life easier for myself. And we're starting with 7. And we're adding -4. Now, either we do it with tiles, and again, that means I'm putting on 4 negative tiles. The action really makes the sentence come alive. Hopefully you can still see that on screen. But my start point was 7, then I added -4. Now, yes, using 0 pairs, off they go. We have an answer of 3. And again, that refers back to the fact that the size of this, the magnitude of it, the absolute value of it is 4. So it could only go 4 that way, or it could go 4 that way. And then if we made that reference to the tiles as well, they can see the absolute value of that -4. The distance we can move on the number line is 4 that way or 4 this way. But it sure as heck is not -11, which is, of course, the frustrating answer. And I'm still thinking back to that year 10 question. I know I'd go for it, but some teachers wouldn't, because they might just think that the pupils will respond negatively. Certainly, if I had a GCSE resit group, I would begin with representation, say, right, we need to re-begin because it didn't work last time, and they'd hopefully be a bit more open to the answers. Okay, so I'm going to leave those on screen for a moment. What I will actually quickly do, at this stage, I should suggest you do a kind of split screen. So if you get at MathSpot, now it's up to you. If you go to manipulatives, you can use the counters for this maybe. And so you have reds and yellows if you like using that. If you want to use those. If you want to use the algebra tiles, and get those one disc, put the labels on. I always like having the labels. Have a play with them. So I'm just going to leave some questions on screen for just a few moments, just if you have a play. While you're doing this, as a reminder, have lots of 0 pairs ready. And also, whilst practicing, think about the language you'd be using. Think about the difference between the adjective and the verb, the act of taking away something. So for this middle question here, 4 subtract -2. Really different maybe. So I'm just going to give you a couple of minutes just to play with those.
On that, Tom, with the difference, there's a comment when using BIDMAS, for example, 5, and the discussion is using negative or -4, add 3.
I'm going to just make a note on that, and I'm going to come back to it. If we give a couple of minutes on this, see if there's any other questions. So 5, can you just repeat that for me?
5. Yeah. And then the discussion is whether to use minus or -4, add 3.
Okay, I'll come back to it. We're just going to give a minute or two for people to play on these, and then see if there's any other questions that come in.
Thank you.
Yeah, that's interesting. I'm just going to sit here quietly. Okay. Obviously, I want to make sure I'm finished by past, and when I start getting excited, I talk more. So I want to make sure that I do get through all the content today. But I really hope you were thinking whilst doing that, what's actually happening? Now, I've looked back, I could see that comment. So let me just go onto the camera again. And this idea here, so let's get rid of that. I think that was the example that was given. Now, actually, on Bernie Westercott's video with Craig Barton again, he referred to this. What is there? If I looked at this bit here, in fact, I want to use a different color, so let's just go over here and find black. If I look at that bit there, that is 5. 1, 2, 3, 4, 5. That could be -4. So it might be seen as -4. Now what happens? Now I've done that, I've got 1 left. And I think actually the comparison of the two, trying to remember conceptual understanding as opposed to just following an algorithm, the comparison of the two I think is very interesting. So if we did say 5 and -4 and then a +3, so I'll just put those back actually. Excellent. And then have another 3. If I put them there, I know I've done them left to right, but that is confusing. If I was, tell you what, let's move my cameras. Let's move my counters around. So I think that's probably wiser. Okay. So 5 take away 4, add 3, or 5 -4 and +3, and those 4 zero pairs still exist, of course. So the answer still remains at 4. And I think you could do the comparison. I would find that very interesting. I think that would be a very useful thing to do in a classroom, to make sure you're comparing what's the same, what's different. I love when you do worked examples. This is going off to a different topic to a certain degree. But when you've got 2 methods, I am going to go do this because it's now in my head. A question, ooh, horrible number. Let's go for that one. Right, 3 loads of 3x plus 2. You could, of course, expand brackets and do 3x plus 6 equals 9, or you could divide both sides by 3 and have x plus 2 equals 3. And I think there's a really nice opportunity in lessons for mathematical reasoning. What's the same? What's different? Does it matter? In fact, no, we will get the same solution, x equals 1 for both of them, but comparing the two. So actually, I think comparing this idea of saying 5 take away 4, or is that just the same as adding -4? Because then what we realise that, let's go for 3 take away 2. Actually, that's the same as 3 take away +2, isn't it? So I think there's opportunities there for conceptual understanding. Let's do some multiplying with integers, and it's all about the language we use here, and I'll be interested to see if people have different opinions on this. 4 lots of 2, 4 times -2. I put some in brackets just for fun. What's the same, what's different about these 2 questions? Now, should we represent some of these? I think what I'm going to do is show you a video. Can we display that one? -4 times -2. A video from Braining Camp. Just go onto YouTube. Now, I'll quickly show it you actually. This website is free at the moment. When I first started learning how to use algebra tiles, this was the website I use all the time. It's fantastic. I really do enjoy the algebra tiles on here. I know this is the one that Van Haar used when he was doing his Maths No Problem presentation, for example. But they've done some videos for us on, they're all on YouTube, just multiplying integers. So I thought I'd show you this one because it was one of the ones I really enjoyed. Tell me if you can't hear the sound, by the way.
Multiplication can be thought of as the first number telling how much to make of the second number. So 2 times -5 is like making 2 groups of -5. There are 10 negative unit tiles in total, so 2 times -5 equals -10. A negative first factor can be thought of as the first number telling how much to remove of the second number. So -2 times -5 is like removing 2 groups of -5. Recall that 0 pairs have no value, so add 0 pairs until there are enough negative tiles to be able to remove 2 groups of -5. After removing 2 groups of -5, there are 10 positive tiles remaining. So -2 times -5 equals 10.
I'm going to pause that just there. I think I've rushed through this a little bit too quickly. I apologise. I'm going to go back to those previous questions in a moment. Let's just see the relationship between these two here. I've got two lots of -5, which you can see, two groups of -5. So hopefully that would be a nice way of showing the positive times the negative. Now this negative times negative is not easy to represent. So the language that she used there was this is the same as taking away. So this symbol here suddenly becomes not negative, but actually the act of minus, subtracting, taking away two lots of -5. And so we added those 0 pairs, and that's how it became positive 10. So let's go to these questions, if I may. I'm just going to make a note of them. So we've got 4 lots of 2 and 4 lots of -2 and -4 lots of 2. Okay. All right, so I'll go onto the camera to represent these. Again, I could use tiles, I could use counters. 4 lots of 2. When we're introducing multiplication, there it is, 4 groups of 2. Spot on. 4 lots of -2, not a problem. In fact, really quite nice and easy. We saw that in the video, I think. 4 lots of -2. Now, I think the next question, I'm going to make sure we can see it on the screen at the same time, was that. -4 times 2. Now, at this stage, I mean, the question I've represented actually, let's put that just below. The question I was doing just before was what? 4 lots of -2, and there it is. You can see 4 lots of -2, 4 groups of it. Now, -4 lots of 2 sounds difficult, but actually, if we've talked about this, commutativity, and I probably have spelt it wrong, and I've written it in a rush as well. I always do. Do you know what? I can speak calmly, but when I write things and these things, I always write them quickly. Commutativity, that's terrible. I'm just embarrassed by that. I'm getting rid of that rubbish. If we talked about commutativity, well, how about changing this here to 2 lots of -4? And that, I think, is actually fine. I think we've got, considering how when we've introduced multiplication, we should be really, really driving home that the multiplication is commutative. So if I represent that the other way around, I've got 2 lots of -4. There they are. And the answer remains -8. Now, of course, I can refer back to the previous question, which, if I recall correctly, was this. 4 lots of -2. But making those relationships between the two again, make those connections. It's not rules. It's not 2 minuses make a plus. It's not if the signs are different, it's a negative answer. That doesn't help us for conceptual understanding. And that's why, in the session I'm doing next week, I'm really looking forward to the language that we use in the classroom. It's really important. I'm going to move on to division with integers. I'm a little bit wary of time, but I'm still quite hopeful we're going to be done by 11:30.
Sorry, Tom, before you move on, there's just a question regarding multiplying.
Yep.
When you're multiplying by a negative, could you say, for instance, -2 times -5, could you say it's 2 times 5, then flip the tiles twice?
Ooh, let's do some flipping. I like it when we come up with ideas of flipping. So 2 lots of -5. By the way, this is one of the reasons why we have visualizers in classrooms. Just being able to do this and talk it through. Yes, I can use the MathBot, and I can use whatever website I use. But to demonstrate, look at me being able to play with it. I think this is a really, really powerful reason why we have visualizers in the room. So your question there, you've asked about -2 times -5. Can you repeat the sentence? Sorry, Amy.
Yeah, sure. So I think it was in regards to -2 times -5. Yep. Would it be the same as 2 times 5, then flip the tiles?
Aha. So as the video suggested at some stage, that is the same as saying -1 lots of 2 times -5. So yeah, that's not a bad idea actually. And that's a nice way of putting it. So you don't flip them, because when you multiply by -1, you flip everything there. Now that becomes very interesting when we do solving equations later on. Nice one. So again, if you didn't like the idea, as she said on the video, let's get rid of that. -2 times -5. You've got 2 lots of -5, and this minus sign here is then the idea of subtracting them all using the 0 pairs. Well, actually, yeah, putting the minus sign is the same as multiplying by -1 and flips them all. Lovely idea. Thank you for sharing that.
No problem.
So division with integers. Again, we consider the words we're using here and how we describe what the calculation is. Right, so what's that say there? So again, what I have tried to do on the previous session, I haven't done it well enough today, is have these available to be able to see. when I do these questions. So we're going to do 8 divided by 4. We're going to model -8 divided by -4. Then afterwards, I'm going to look at those questions, -8 divided by 4 and 8 divided by -4. Now, then obviously there's a lot of difference between those, but we're to consider the words and how we describe those, and then I'm going to watch a video from Braining Camp again. So I'm going to try those. Oh, I have 8 ready. That was nice. Now, we talk about grouping. Well, we talk about different things, or do division, but that first number sentence here, 8 divided by 4, could be said as 8 divided into 4 equal groups. It could be, how many 4s go into 8? And so there's 2 different numbers, ways you can describe that, and interchanging between them both, I think, is really important, because the right situation, I mentioned earlier on the right representation for the right situation. So 8 divided by 4, how many 4s go into 8? Now, what about this question here? -8. Here we go. How many -4s, groups of -4s, are there in -8? And I think that then becomes that little bit easier. So how many -4s are there in -8? Well, I've got one -4 here, and I've got another -4 here. So I have 2 groups of it. And I think the language there is quite important. So you could say, as I said before, into -4 equal groups. Do you think that would sound right? It just doesn't seem to feel correct to me. So interchanging between the language we use with division. So that first one again, 8 divided by 4. 8 divided into 4 equal groups. Or how many 4s are there in 8? And I think when it comes to the second question, -8 divided by -4, we're asking the question, how many groups of -4 are there in -8? And we can see there are 2. Let's try the next one. -8 divided by 4. Well, what you might say is 4 groups. So how much is in each equal group? In each equal group is -2. So -8 divided by 4 equals -2. This one is one that just doesn't feel right to me. So thankfully I went on to Braining Camp and I watched the video online, and I just missed the one I want to watch. This one here, dividing integers, I thought this version was interesting.
Division can be thought of as finding how many groups of the second number can be made from the first number. So dividing +6 divided by +3 is like counting how many groups of +3 can be made from +6. There are 2 groups, so +6 divided by +3 equals +2. Dividing -6 divided by -3 is like counting how many groups of -3 can be made from -6. There are 2 groups, so -6 divided by -3 equals +2. We can use these results to find some related divisions.
Making connections.
Since +6 and -6 are opposites, the number of groups of +3 that can be made from -6 is the opposite of the number of those groups that can be made from +6. Similarly, the number of groups of -3 that can be made from +6 is the opposite of the number of those groups that can be made from -6.
I'm going to just scroll back just a little bit. There we go. So it talks about opposites, and I mentioned this when we were introducing negatives earlier on. This is unquestionably the most uncomfortable part of it for me, because I'm not fully convinced. But it is talking about the fact that negatives are opposites to positives, and we can derive these results from these results. Now, I love talking about derived facts, and I regularly do it, that we don't do enough of it in a classroom. If I know one thing, then I know something else. And those of you who are on Twitter, and hopefully we'll be talking positively about this afterwards, again, at mathematics, I shared something yesterday about if I know, then I know. And Amy's going to nod with me. Remember when we first met, Amy? It was one of the first things I sent you that I was going to do with our joint class. If I know 7 times 8 equals 56, then I know 56 divided by 7 equals 8. I know a 7th of 56 equals 8. I know an 8th of 56 equals 7, and so on. Amy, you know what I'm talking about, don't you?
Yes.
And it's awesome, isn't it?
Yeah, and it did highlight a lot of gaps in that class.
So go on to Twitter to go and have a look at that. But it's those making connections, and if we're deriving one thing from another, we've got proper mathematical understanding. And again, that is the national curriculum. We're trying to get them to understand. So I think I've gone through a couple of those. -8 divided by -4. How many groups of -4? Oh, sorry, pardon me. That was the one I represented before, wasn't it? -8 divided by 4. If you have 4 groups, how many would be in each group? Very interesting. Maybe, again, different, the right language for the right situation. So then, that more or less ends what I was going to do with integers, but I'm going to be using integers in some algebra tiles now. So substitution, going back to the algebra tiles. And let's do a couple of examples here. So I'm just going to make sure I have a note of these. So if x equals 3, I've got 2x plus 5, and I've got 3x minus 2. And I'm also going to have x equals -1. So let's have a look at these questions using substitution. And I'll go onto the camera. So I talked earlier on about the importance of being able to represent. And here are the 2 expressions we're going to talk about. 2x plus 5. I'm just going to get rid of the other writing not to put you off. 2x plus 5. So I'm going to represent 2x plus 5 and the importance of the pupils being able to do that. There it is, 2x plus 5. I've got 2 x tiles. It doesn't matter if I rotate them. They're still x. And these 5 tiles here. Now, substitution, just like, what I refer to is when I remove a footballer, you replace him with someone else. You're substituting. And I'm going to replace the x with 3. So I'm going to remove an x and put 3 tiles in. And I'm going to remove another x and put 3 tiles in. No, I've made them a mess. Yes, absolutely. But how have I got now? I've got 3, 6 plus the 5. So let me just check. Just go through all my notes on that. 3 plus 3 plus my 5. I'm making some horrible writing errors today. Really bad. I'm kind of wishing this wasn't recorded. 3 plus 3 plus 5 equals 11. Now, what's actually happened, and now this is where I talk about concrete pictorial abstracts, and I mentioned it earlier on, we've got to make sure we relate that to the abstract. So I'm running out of paper. I thought I had loads of spare paper today. Oh, dear me. Right, let's just find another thing to write on. So what did I have? I had 2x plus 5. And I replaced the x with the 3, and you saw that in the tiles, and you show them what's happened in the abstract. I replaced the x with a 3. Don't just do it in by itself. Make sure you're showing what's going on. So 2 lots of 3, of course, and there we've got our solution. 2x plus 5 again, but this time, so I'm just get the 2x plus 5, and they can see it happening. They can see the x. If I'm going to say x equals -1, I'm going to replace that x with a -1. I'm going to substitute, using the proper mathematical word actually, with -1. And they can see it happening. And oh, we've got some 0 pairs. Goodbye. And the solution is 3. I make sure I relate that to the abstract. This is not to replace the abstract. This is to be to support its understanding. -2 plus 5. And of course, earlier in our journey, we'll have done adding of integers, and we'll have seen that that will equal 3. I think for substitution especially, it's a beautiful topic to really show what's going on. You are substituting, you are replacing the x tile with a with the value you want. There are limits, and I've said it a couple of times today, the right representation for the right situation. I am not happy yet with a way of doing these questions. Okay, if x equals 3, then what is 1 plus x squared? What I would then do in my personal journey, and if someone's got a better one, please throw it out there. I have already represented using the brackets what I did for 2x plus 5, where I put the 3 into brackets. In fact, I'll go onto the camera for that. So 2x plus 5, I've changed the x for a 3, and so I showed it with the tiles, and then I've done it with the abstract form. And so maybe that's the way I would do it. What did we do before? We substituted the x, didn't we? And we replaced it with a 3. And so that's how I would do it. I haven't come up with a way that I'm really happy with demonstrating it using tiles yet. But that's something that I wanted to make sure I challenged. And again, that's why we remember CPA. It's not the point to replace the abstract, but to build to the abstract and make connections between the concrete, the pictorial, and the abstract. I'm going to move on to solving equations unless there's any questions. Have we lost Amy? Okay.
Yeah, Amy's internet's gone down, Tom, so she's just had to disappear for a while.
Thank you, Producer Liz. Now, Producer Liz, you're in charge. Thank you for doing that. Solving equations. Well, should I use algebra tiles? And I had an email about this from a colleague yesterday. And I go to the right representation for the right situation. So let's argue this. 2x equals 8. Well, I think that's really useful. Having taken from the part-part whole in primary, you can see you've got these two x's here. The width of them, the length of them, sorry, is the same length as 8. So if they're the same tile, then x would equal 4. I think there's reasoning that just comes from that vision. And I've taught this to a class once where I just gave them the pictures and said, what does x equal? And they said 4. I said, why do you know? And I haven't given them the equation, I've just given them a picture. And they were able to pick up, and then I made a link from the bar model to the equation. 2x plus 1 equals 9, and there it is, being able to represent it again. And again, I made some of these through MathSpot, so go and have a look at this on the bar modeling section. 2x plus 1 equals 9. In fact, it was this question I gave that class, and they were able to interpret the fact that x must equal 4. I think the key here being the length of the bars being the same. The right representation for the right situation. Be willing to change between bar modeling and algebra tiles. So what about this one? 2x plus 1 equals x plus 9. There it is represented. This will put some of you off, the fact they're not exactly the same. I apologize. But if I cover up, I just want to put my hand over the screen. If you cover up the x's on the left-hand side here, if you cover that up, you suddenly got x plus 1 equals 9. And you make the connection. What have I done? I've taken away x from both sides. So x plus 1 equals 9. What about this one? And this is where some people don't like bar modeling, where they think the negative tiles become a little bit confusing. So solving equations, should I be using algebra tiles? Well, do you know what? The NCETM have again come up with a video for us, so I wanted to make sure you saw these today because they are useful for you to go away and use in your teams. As it says here, Mastery Professional Development, these have been created for you to use with your teams. So I'm going to let it model a 4-minute video on how to solve equations. Some of them you might like. Some of them you might think, you know what, they're not for you, but let's have a look.
Solving equations using only abstract numbers and symbols can leave some students confused. Algebra tiles help students to visually understand how to solve linear equations. Let's look at some linear equations to see how algebra tiles can help when solving them. First, an equation that shows how we can remove tiles from both sides. The equation x plus 7 equals 3x plus 1 has positive x terms and positive number terms on both sides. We can use the tiles to represent the equation, separating the two sides of the equation with a line. It might be helpful to put an equals sign on the line too. Subtracting terms from both sides of the equation can be shown by removing tiles. It is important to see how the equation changes as this happens. We can remove an x term from each side and write the new equation below. We can also take 1 from both sides and write the new equation. The final step is to arrange the tiles into 2 equal groups, 2 being the number of x's. This shows a solution of x equals 3. Now let's look at using the tiles to create 0 pairs. The equation 2x minus 3 equals 6 minus x involves negative terms, so the red side of the tiles can be used. Where there is a negative x, we can make a 0 pair by adding x to both sides. The 0 pair has no value and can be removed. We can now write the new equation. 0 pairs can also be created on the left-hand side by adding 3 yellow 1 tiles to both sides. The 0 pairs can be equated to 0 and removed. This gives the new equation 3x equals 9. The final step is to arrange the tiles into 3 equal groups, 3 being the number of x's, showing a solution of x equals 3. In this next example, let's look at an equation that includes brackets. Algebra tiles can be used to represent the x plus 2 expression inside the brackets 3 times. We can then write the equation with the brackets expanded. We can simplify the left-hand side of the equation by identifying and removing 0 pairs. We can now write a simplified equation. We can remove the unwanted number on the right-hand side by adding 1 to both sides, creating another 0 pair. Let's remove these 2 tiles as they equate to 0. We can now write a new equation step. Finally, let's look at an equation that has a negative solution. 8 subtract 2x equals 2 subtract 4x. We can use algebra tiles to represent the equation. There are many ways to solve this equation. One strategy is to subtract 2 negative x tiles from each side and 2 1 tiles from each side. There are several ways to arrive at the solution from this point. Dividing by 2 will give 3 equals negative x. The final step could be to multiply both sides by negative 1. This can be shown by flipping all the tiles to give the solution. Let's recap the ways that we can use algebra tiles to help us when solving linear equations.
I think that last one's a very, very powerful and maybe the time when algebra tiles are probably more useful when it comes to solving equations. So I'm going to represent that last question again. There it is. The question, the last one they did was 8 take away 2x equals 2 take away 4x. Well, what about multiplying everything by negative 1 at the very beginning? And if you multiply everything by negative 1, that's a lovely reminder that everything changes. Everything. And do you know when we have that those opportunities in equations where people don't realize it's every term? Well, with algebra tiles, they would see multiply everything by negative 1. Look at everything flip. So on the left-hand side here, the negative x's become positive x's. The positive 1 become negative 1s. Over here, the positive 1 become negative 1s. And look at that equation suddenly. X take away 8 equals 4 take away 2. And suddenly it looks easier. That's where I think algebra tiles have a really, really positive, a strong opportunity to be used positively. I think I'm going to give you a chance to have a look at those quickly. I'm not sure if Amy's back in the room, so what I might do is just have a look through the chat. So I'm just going to give you a chance and leave these on screen and give you a chance just to read, play those equations, have a go on MathSpot with a couple of those, about 3 or 4 minutes, and then we've only got about 2 minutes left as well.
Tom, sorry, while that video's on, someone's asked how would you use algebra tiles to solve when the answer's not an integer, if you wanted to talk through that.
I'll look at that afterwards if you don't mind. Okay. Great question. Okay, again, while you're doing these, think about the language you might be using. If you like the idea of multiplying everything by -1, are you doing the same to both sides? I can see somebody on the chat referred to balance, doing the same to both sides. And maybe that's the importance of that equal sign. Equal doesn't mean this is the solution to. That equals sign means is equal to. Both sides are the same, so we have to do the same to both sides to make it balanced. So in reference to you saying that, Justine, I think you're right, but that's the importance of what they think equal sign means. It doesn't mean the solution to. That's really important. Something that's never occurred to me until maybe the last year. Are we all challenging whether that symbol means the same as, equal to? That's why we have to do the same to both sides. That's how you stay balanced. Gainer's asked, would you show the class the different ways to solve? I made reference to comparing two methods, and I think that's really important. I made reference earlier on when you were solving expanding brackets, was it? I would show both ways. Absolutely, and compare them. The fact they both become with the same solution, and you're giving more tools to the toolbox, aren't you, if you give them more than one way of doing it? So personally, yes, I would. I see a question you referred to, Liz, and thank you for stepping in, by the way, really appreciate it. And by the way, Amy, I wasn't paying Amy for this, just to make sure everyone else knows, this is all free, and I don't know, Amy told Liz that she was being paid to try and wind her up. No, this is all free because I'm enjoying it, and hopefully everyone else is as well. How would you use this for solving where the answer is not an integer? And now I believe, if I go to MathBot, and let's see if I can actually just get off screen, there we go. I believe he has started to make it so you can split them. Aha! So I haven't played with this a lot, but if I just go for this this one tile, I can split it and have a half. Or I can split it. If I put that back, can I split it again? Ah, look, I've split that quarter. Okay, so that's where I maybe argue the possibility to be able to split those tiles when you show them. Of course, so hopefully that will be one way for you to have a play. So please, in your own time, go and have a look at splitting the tiles. Great question, and one that didn't occur to me for a long time. One that I want to look at the camera. So if I may, what I would say is, when we did the same, oh, that's a horrible choice. Did you notice they did 3x equals 9, and you don't want x to equal 3? What a poor choice, because I've already got a 3. I don't want the solution to be that. So let's go for 93 instead. So that this coefficient is the same as the solution. When you're doing the same to both sides, actually, this is an opportunity maybe to show 93 over 3. And so if I was then doing, let's say, 3x equals 7, x equals 7 over 3. And that wonderful reminder that you can have a fraction answer. You don't have to find out what 7 over 3 is. 7 over 3 is a number that we can use. We don't have to have the decimal answer. A huge misconception we seem to allow our pupils to get. Nearly finished, so a couple of more things to finish, and I've got a great link for you. It is absolutely superb. It was written 5 years ago. And for those of you who have seen it through to the end, and there's nearly 100 of you who have been over 100 today, so thank you for tuning in. I've got a really, really useful link. It's got loads of ideas how to use algebra tiles. Other options to algebra tiles. Well, as I said, the right representation for the right situation. I don't have these physically, but on MathBot you can see the algebra discs. The x squared looks like an x. The same size, they've chosen different colors. I've seen these used in classrooms. I quite like them. I think it's the follow-up to the algebra tiles. Remember, algebra tiles show the kind of the area of an x. I'm going to hold them up on screen to show that the x squared is very much different to the x. I think that's really important when you first meet algebra. I hope you can hear me, because suddenly I've got a hailstorm going around and I'm kind of in my garden shed. So hopefully the sound is still good. So yeah, another option to algebra tiles. Well worth looking at those. I've seen them available on eBay. I noticed some people discussing where you can buy these counters, the red yellow counters. You can buy them from TTS. I know you can buy your tiles from TTS as well. So just shop around to make sure you're saving your money. So a quick reflection. How would we use these in lessons? Do you know what? I'm going to change those words straight away. How would we use those in learning journeys? Because I don't like thinking about what we do as a lesson, 60 minutes. Some things take longer than others to learn. A great lesson from Mark McCourt's book. And so where would I use these in learning journeys? I'd use them at the beginning. Concrete pictorial abstract. I want the kids to play and get the conceptual understanding. But of course, refer back to them as often as possible, which is why I did a slide at the very beginning, and I referred to it a few times. Make sure the pupils are concrete or confident at using the tiles and that representation. X+3, what does that mean? So during which phases of the learning journey? Absolutely at the beginning, but yeah, referring back to them continually whenever you need to. So if pupils got stuck with the abstract, you bounce back to the pictorial to remind them. Now, I really want you to look at this link. I will put it on the chat myself, assuming Amy's now able to. It goes through a number of scenarios where algebra tiles can assist you. So if you look up, if you want to Google it yourself, Great Maths Teaching Ideas by William Emeny, not Enemy, Emeny. But I will put that link in the chat room in just a few moments. There is a load. In fact, you know what? I think I can quickly share it. I think I've got it on screen. There it is. So from counting to completing the square, he talks about some bar modeling, but then he does a lot of algebra tiles for you as well, talking about zero pairs, directed number addition. If I scroll down, number of division as well, multiples, collecting like terms, substitution, solving equations, a really lovely page. Brilliant stuff. And I'll tell you what, in maths teaching at the moment, people are sharing so much nice stuff for free. It's wonderful. Just to show a couple of my favorite things from it, completing the square. It was my first head of maths who made me realize that completing the square actually meant a square being completed. So and I know Mr. O watched my session last week, so hello Mr. O if you're watching this week. Thank you for the help and the difference you made to me. There is the square. Look at that there. We've got x+3 times x+3, and there's an additional 2. So you can see the square, add 2. Suddenly completing the square isn't just an algorithm, it's conceptually, it can be understood. Wow. And I still meet teachers, I've been teaching for years who've never come across that. And again, when I learned it, I'm like, wow, blows your mind. Factorizing, difference of 2 squares. Now, I've said that if you can factorize, you can make a rectangle. And that, please look back at last week's session for that. Well, I can't make a rectangle or a square with those tiles, but I can if I add some 0 pairs. And look at that, x+3, x-3. Really nice way of representing it. So at this stage, I thank you for tuning in. Again, on Twitter, if you want to share this with people, I'm at Manematics. I'm doing it for free because I'm enjoying it. Please be nice if you want to share some stuff, but I really want this to be popular because A, I'm vain, but I want it to be used. I'm hoping to get people talking about maths teaching and hoping they're enjoying their jobs. Please do share this and my other sessions with colleagues. Sign up for the next one. I'll put that link in a few moments' time in the chat box, but also on the email you'll receive later on today. You'll receive an email from Eventbrite, so please check your junk mails. There will be a link to my previous ones and also a link to this next one. I'm doing it on Thursday next week because in case you haven't realised, next Friday is bank holiday. So speak like a mathematician, the importance of the language we use. Looking forward to that session. I really enjoyed planning it.